Welcome back to the Python tutorial series. So far, we have built our foundation in Python: variables, data types, conditions, loops, lists, dictionaries, functions, and modules. Okay, so if you haven't watched these so far, please go and watch them first. Okay, now we are moving on to something very important for data science and machine learning, which is Numpy. So Numpy basically stands for numerical Python. Okay, it stands for numerical Python. So if you're planning to work with data, machine learning, deep learning, scientific computing, images, signals, or even AI, then Numpy is one of the libraries you should be comfortable with. So in this tutorial, we are going to understand Numpy from basics. We will learn what Numpy arrays are, how do we create them, how to access and manipulate elements, how vectorized operations actually work, and then we will move towards concepts such as shaping, broadcasting, filtering, statistics, and access. And importantly, we won't just look at the theory. I will demonstrate everything practically in the Google Colab so that you can follow along and run your code. Okay, so let's get started. Why NumPy? Okay, so before we even learn NumPy, let us understand why we actually need NumPy. Okay, so Python already give us list. Okay, we have list in Python, right? So why introduce another data structure? Why do we need that? Suppose I have a list containing the marks of the students. Okay, and I want to multiply every mark by 2. So with a normal Python list, what will we do? We will generally need a loop, right? With NumPy, instead, we can perform the operation without needing a loop. We can directly operate on the entire array. So this concept is called as vectorization. So instead of telling Python, take the first element, multiply it, then take the second element, multiply it, and then the third, we can simply say multiply this complete array by 2, and NumPy handles this operation efficiently. So this is the one of the main reasons NumPy is so important in numerical computing. It also provides optimized memory storage and a large collection of mathematical and statistical functions. And there is another important point. Many libraries that will be used later in the data science are built around NumPy only. So learning NumPy gives us a strong foundation for pandas, machine learning, and scientific computing. Okay, so let's try doing the same thing that I'm doing here in the Google Colab. So what I'm doing is, there is a simple Python list which is having numbers. Okay, so if I want to multiply every number by 2, I'll explicitly have to use the loops. Okay, any of the loops. Okay, like for loop here, for I in range the length of these numbers, I will take every element of the number and multiply it by 2 and store it back. Okay, what if I had used NumPy arrays? I'll simply convert this list into a array, which is np.array. Okay, why np? Because I'm importing NumPy as np. Okay, so now my a is not a list but a NumPy array. So what I can directly do is a into 2, and it directly gives me every element multiplied by 2. Okay, let us do it in the Google Colab. Okay, so shift enter. I have imported NumPy as np. So my numbers here are, say, a list 10, 20, 30, 40, say 50. Okay, so these are the numbers. Okay, so what I'll do is I'll simply take another list, maybe say result. Okay, and then what I'll be doing is, what I'll have to do is, for every element, for say n in this numbers, list numbers. Okay, what I'll do is, for loop, the iterator would be result dot append. We did it, how to append something in list. Okay, so I am multiplying everything by 5. Okay, now it will give me every number multiplied by 2. What if I have used instead of list the array? So what could I do is, first I need array for that. So np dot array, np because I have used the alias. Okay, so numpy as np. Now I'll provide my list here. My list name is numbers. Okay, and then I would simply write in print A into say 5. Every element multiplied by 5. Okay. So it will directly give me a list which is a NumPy array, and the difference here is very clear. If you check basically the type of these two, type of numbers, okay, and then type of this NumPy array A. Okay, so if you print them, first is list and second is NumPy array. Okay, so now let's go back here. Now let's create our first NumPy array. So first we need to import NumPy like we did. So import NumPy as NP. This is the standard convention. Here is NP is our simply an alias. Okay, so the most common way of creating an array is using np.array. So we can use a Python list to np.array, and NumPy automatically converts it into a NumPy array. But NumPy gives us several other useful functions as well. For example, np.zeros. If you want to create an array filled with zeros, you can directly use np.zeros. This 2 by 3 is its size. Okay. Then you can also use np.ones, which is basically an array filled with all ones. Okay. np.arrange, it is basically useful when you want a sequence of values. Okay. And np.linear space and linspace, it is basically useful when we want to have a specific number of evenly spaced value between two limits. For example, from 0 to 1, I want like there are 5 numbers which are equally spaced. Okay. So this is how we use that. Okay, so these functions become extremely useful when we start working with the real data sets and mathematical computation. So let us try doing the same thing that I am doing here in Google Colab. Okay, so we have already imported NumPy, so I won't be doing it again. So let us do creating the arrays. Maybe name of the array is 0. So np dot zeros, if I want to create say 2 by 3, okay, and let's print zeros. Let us see what it has created. Okay, I basically forgot to give brackets here. It's the function and the size here. Okay, so it gives me 2 by 3 array of 2 rows and 3 columns, array of all zeros. So you can also do ones, which is your np dot ones, and it would be maybe sizes 2 by 3 again, and it will give you ones. So let us print it. Okay, so because it is an array, it has given all the values as ones. Okay, let us try to use the arrange function. Let me create an array where I will write np.arrange. What I want to arrange is all the numbers from 0 to 2, 0 to 10, and every number separated by 2. So every second number to be printed. Okay, so now let's print this array. Okay, there is a spelling mistake in arrange. So now it has printed all the numbers between 0 to 10 separated by 2. Okay. Now let us try another function which is linear space. So basically np.linspace is the function that you will be using. Okay. You want all the values between 0 and 1, and you want 5 values which are equally separated. So you can expect 0, then 0.25, then 0.5, 0.75, 0.1, and 1. So let us see what it gives. Okay, these are the values. Okay, so now what if you want to create an array containing numbers from 1 to 20? Array containing numbers from 1 to 20. This you will be trying on your own. Okay. So let us understand the array properties. So creating an array is only the beginning. When working with the data, we often need to understand the structure of the array. Okay, so NumPy provides us several useful attributes for this. So first is ndim, which is the number of dimensions. It tells us how many dimensions an array has. Then we have a shape function. Okay, shape tells us the size along which the each dimension. For example, if we have 2 rows and 3 columns, then the shape will be 2, 3. Okay, then is size. Size tells us the total number of the elements. So if the shape is 2 by 3, then the number of elements would be 6. And then there is another function called as dtype, another property of array. Dtype basically tells us the type of data which is stored inside the array. Okay, so these properties are extremely useful when debugging your code, because many NumPy operations depend upon the shape of your data only. Okay, so let us try to create this array 10, 20, 30, 40, 50, 60. So it has 2 rows and 3 columns. So number of dimensions are basically 2 and the shape is 2 by 3 and number of elements would be 6. Okay, let us try to do it in Google Colab. So let me create A, which is numpy.array, and the array I want is, first row would be 10, 20, 30. Okay, and then second would be 40, 50, 60. Okay, so this is my array that I have created. Let us try printing it first. Okay, so this is 2 by 3, which we can directly see. Now let us try to print the dimensions. Okay, so dimensions would be a dot ndim, which is number of dimensions. Okay, okay, it is 2-dimensional array. Then the shape would be, let us see, print shape, and then shape would be a dot shape. Okay, so it will give me 2 by 3. Then size would be the number of elements in it. Okay, so let us see the size, which is a dot size. Okay, now because these are the properties of the array, these are not basically the functions, so we'll directly use the dot operator, not the brackets. Okay, we can also check the data type of the elements inside this NumPy array. So data type would be a dot d type. Okay, so it is int 64. So there is a quick challenge. Let us see if you do, maybe another array is b, numpy dot zeros. Okay, and we created 4 by 5. So you will have to tell the number of dimensions, number of the shape of this array, and the size. So what do you think the size would be? So please let me know your answer. Okay, now let's move on to indexing and slicing. Okay, it is one of the most important skills when we work with arrays, which is indexing. Okay, just like a Python list, if you remember, NumPy uses zero-based indexing. That means the first element has index 0 and the last element can be accessed using the negative indexing, same like the list. We can also use slicing. Okay, so here the first element is 10, so we used index 0, and -1 is for the last element, which my array is 10, 20, 30, 40, 50. And if I use this slicing 1 to 4, so what will it basically include? 1:4 starts from the index 1 and stops exactly before index 4. So the position of stop, the stop position 4, it is not included. The same concept extends to 2-dimensional arrays. There we provide the row index and the column index. Okay, so this becomes extremely important when working with matrices, images, and other data sets. Okay, so let us try to do this same thing in Google Colab. Okay, so let me create an array A, which is numpy.array. So let's take it 10, 20, 30, 40, and 50. Okay, then let me print the first element. So how to print the first element? A of 0. Okay, then if I want to print the last element, it would be print a of, and then it would be -1 to access the last element. Okay, 50. And the same that we did in theory, print a of 1 till 4, and 4 is not included, so it is 20, 30, 40. 1 first position is 20, 10 was 0th position. Okay, okay. Now let us do matrix. Okay, so my matrix, let me create as np dot array. Now it would be a 2-dimensional array. So in 2-dimensional array, let me create 1, 2, 3, and maybe second one is 4, 5, 6. Okay, so this is the matrix. Now what I want is, I want to print element numbers, say 0, 1. So what would be 0, 1? 0th row and first column. So what do you think it would be? Okay, so because there should be square brackets, that's why it throws the error. Okay, so 0, 1 would be element number 2. Okay, now what if I want to access first column and second row? So I would write 2, 1, row 2 column. Okay, what if I write print matrix, and then I want to access, okay, let us see what this thing prints. So it will print the column and all rows of that element. So for printing a particular column, for row you will write column, which is all elements and the column number. Okay, so it will print the column. Okay, now column number 1 is printed. If I want to print the row, okay, so let's see how to access row number 1. So my row number 1 would be 0, row number, and all elements of that column, right? So 1, 2, 3. This is printed. Okay. So if I want to extract 20, 30, and 40 from the numpy array, for example, my numpy array is np dot array, and then it is 10, 20, 30, 40, 50. Now in this, if I want to extract 20, 30, and 40, what would be the code be? How to access that? Let me know. Okay. Now come back to the vectorized array operations. Now we have come to one of the most powerful features of NumPy, which is vectorized operations. So let's say we have an array which is containing 4 numbers. We can add 5 to the entire array. Okay, so we can simply add 5 to the entire array plus 5. Now it gives me 15, 25, 35, 45. Okay, we can also multiply the entire array by 2. Okay, so this entire array is being multiplied by 2. So we can also square every element. We can even perform comparisons, element-wise comparisons. So notice we haven't used any loop. Okay, NumPy applies the operation element by element internally. So this makes our code smarter, cleaner, and usually much faster for numerical overload. So this is my array. I simply write a plus 5, a into 2, a square 2, and a if a is greater than 25. Okay, let us try to do it here. Okay, here is my a. Okay, now what I'll be doing is, let me print my NumPy array plus 5. It must give me every element with plus 5 value. Now print, say a into 2. Okay, so every element must be multiplied by 2. We can also do the comparison. So a greater than 25. So it will give me true, false for each element. Those who are greater than 25, it will give me true. Those who are less than 25, it will give me a false. If we compare it with the loops and maybe the list, so I'll have to use a for loop and do it every time. So in NumPy arrays, we are having the same result, but NumPy allows us to express the operation much more naturally. Okay. So our next concept is reshaping. So sometimes our data set is in one-dimensional form, okay, but the algorithm or the operation we want to perform requires a two-dimensional structure. So that's where reshape becomes useful. So here we have 6 values, 1, 2, 3, 4, 5, 6. Okay. So we can reshape them into 2 rows and 3 columns, or 3 columns or 3 rows and 2 columns. The important rule is that the total number of elements cannot change. 6 elements, they can be arranged 2 by 3 or 3 by 2, but we cannot reshape 6 elements into something containing 10 elements. So that is a very common concept in machine learning and data pre-processing. So let's try to do that. Okay, so maybe my array A is equal to, say, np dot arrange 1 comma 7. So it should give me all values between 1 to 6, and then let us print A. So 1 to 6 I have done. Now I want to create a matrix which is from the same array. Let us reshape the same array in 2 by 3. Okay, and then let's print this matrix. So now it is 2 by 3. Okay, so what if I try to reshape the same in maybe say 4 by 2? Because we have 6 elements, I cannot have, so it will definitely give me error. It will simply give me a value error. Okay, so we cannot reshape array of size 6 into 4 by 2. Another important thing is we can do flatten. So my matrix, which is 2 by 3, now I want to flatten it into a 1D array. So what I'll be using is flatten. Okay. So it is now become 1D array. We can also perform maybe A dot reshape into 2 by 3 dot transpose. For transpose, this is simply dot T. Now it has given me 3 rows and 2 columns. Okay. So this was all about reshaping. Now let's come to broadcasting. So broadcasting sounds complicated when you first hear the word, but the basic idea is quite very simple. Broadcasting basically allows NumPy to perform operations between arrays that don't have exactly the same shape. So as long as their shape is compatible. Okay. For example, we can have a 2 by 3 matrix and a one-dimensional array containing 3 values. Okay. So NumPy automatically applies those 3 values across the rows. Okay. So this avoids manually repeating the values. So broadcasting is one of the reasons NumPy operations can be both powerful and concise. You don't have to manually construct a larger array just to perform the operation. Okay. So if I have these 3 elements and this is my 2 by 3, so it will simply add it here and giving me the same shape 2 by 3, but these elements are added row wise. Okay, so let us try to do this in Google Colab. So here A is my say NumPy array. Okay, I already have this 1, 2, 3, 4, 5, 6. Okay, now my another one B is equal to, which is NumPy dot array. Let me say it is 10, 20, 30. Okay, let us print A plus B. So it basically adds 10, 20, 30 row wise. Okay, so result would be 11, 22, 20, 33, and in the same way in the second row. Okay, so if I print the shape of A and B, let us see what it gives. So A dot shape must be 2 by 3, right? And B shape would be, shape of B would be, it would be only 3, 3 comma 1. So 1 it generally skips. So let's see what it prints. Okay, so here are the shapes. Now is advanced indexing. So let's make indexing more powerful. Suppose I have a student marks and I only want the marks which are greater than 10. Okay. So instead of writing a loop, we can create a condition. So this condition itself produces a Boolean array. Then we can use that Boolean array to filter out our original data. So this is called as Boolean indexing. We can also provide a list of indexes to select specific position. So this is also a fancy kind of indexing. These techniques are extremely useful when filtering the data sets. Okay. So we'll be doing the same. We have an array. We have given a condition. Give us A where A is greater than 10. Okay. And it will give me the places where A is greater than 10. So you can check the condition where A is greater than 10. It gave position number 0, position number 2 and position number 4. And then I print A of this, which is position number 0, 2 and 4. Then it will print this. Let us try to do the same in Google Colab. Okay. So maybe A is another and P dot. Let us simply use A is equal to A dot flatten. Okay. So my A is 1, 2, 3, 4, 5, 6. Let me take a condition which is equal to A say greater than 3. Okay. And if I print this condition, it will give me the Boolean values of where actually this condition satisfies. Now I can extract the elements from A of say condition. Okay. So it must give me all those elements where the condition was true. And if we want to do it all together in just a single step, so you can simply write say A and then A may be greater than 2. Okay. And it will give you all the elements where A is greater than 2. You don't have to write first the condition, then A of condition and then do it. Okay. So let us try fancy indexing once. Maybe say print A of 0, 2, 4. So it gives me the elements where it is satisfied. 1 and 3 and 4. These are the values. Okay. So if you take a real world example, for example, there is a list or we have Numpy array marks. So let me convert this into Numpy array first. And P dot array, my list is say 45 marks, 78, 92, 33, 88, say 61. What I want is, I want to print all the marks where marks is greater than equal to say 60. Okay. So it will give me only those elements. So how would you select students scoring below 40? Let me know. How would you rewrite the code so that you can select the students which are scoring below 40? Next is iterators and generators. Now let's briefly connect Numpy with another Python concept we have already learned, which is iteration. So Numpy provides ND-ITR. So ND iteration. Okay, so this is for iterating efficiently through array elements. This can be really useful when we specifically need to process elements individually. Okay, but remember that if a vectorized Numpy operation can solve the problem, it is generally preferable to use that instead of manually looping through an array. Okay, we can also use the Python generators where we want to produce values one at a time rather than storing everything in memory. So this basically becomes useful when dealing with large amounts of data. Okay. So we have Numpy array and we can iterate it using np.nditr and print the elements whatever we want. For generation, we can use the generator function where we define any function and we simply write yield and it generates for us. Okay. So what is the use of this yield or the generator? It doesn't generate everything at once. It basically does it one by one. So we don't have to store everything at once. So it saves a lot of memory. Let us do hands-on in Google Colab. Okay. So for example, my array A, np.array, say 1, 2, and in the next row it is say 3, 4. Okay. Now what I do is for say x in np.i np.n d iter of a. Okay. So I will simply print x. So these are all the elements which will be printed. Okay. So it is printing all the elements. Okay. Now how do we use the generator? So the same we did it in the theory. Let us write def function for writing my function. Okay. For square of say n square function I'm defining. Now I'm writing for I in range. Range function we have already used. Okay. So I in range say, and what I want is I want to yield everything powered by 2. Okay. Now for any value in square of my argument, which is say let us 5. Okay. And I want to print the value. So what it is doing, it is taking the numbers from 1 to 4 because I have passed the argument 5, and it is yielding the square of it. Okay. So if we do basically g, say let us say g is equal to square of 5 generator, g is my generator, square of 5, and if I am simply printing g, it is basically generating a single object. It doesn't immediately create the complete list of values. That is the major benefit. Okay. Next is universal functions. Okay. Numpy also provides a large collection of universal functions commonly called ufuncs. Okay. We call it as U for universal, funcs for functions. Okay. These functions operate element by element on the arrays. For example, we have square root, exponential, algorithm, absolute value, sine, cosine. The most important thing here is that we don't have to write a loop for each element. Numpy applies the function efficiently across the entire array. So, okay, for example, I have a NP array. So, I can simply write NP dot square root of my array. It will do square root of every element. NP dot log of my entire array. It will do log of every element there. Absolute. You can do any function. Okay, these are handful of functions provided internally by NumPy itself. Okay, so let us try to see 1, 2 functions here. Let us see what A is. Okay, is it 1, 2, 3, 4? So what I can do is let me print np dot, let me take log values of A. So it has given me log value of the entire array. I don't have to loop through it. Okay. So if I have angles, I can take sine value, cos value. Okay, all these functions are available. Then we can do statistics directly on the NumPy array, and we use for something extremely practical. Suppose there are marks of 5 students. Okay, we can calculate using total using the sum function, average using the mean function, the middle value using the median, minimum, maximum using min and max. We have standard deviation, which tells us about the spread of the values. These functions used constantly when performing exploratory data analysis. Okay, so if you have array, okay, you try it on your own. Given this array, you can directly apply the function mean, standard deviation, max. You can use min function, you can use percentile, variance, cumulative sum, median. Okay, you can use all these and do the statistics part on your own. Okay, so if you want, let us do Google Colab. Okay, so let us take marks Yeah, okay, I have already something in marks. Let me print, maybe say average marks, which will be marks dot mean. It will directly apply. Okay, I can also have highest marks. Okay, let us take highest. So it will be marks dot max. So this is quite simple to do, right? Similarly, you can do lowest marks using min, standard deviation using STD, 75th percentile. Let us maybe do percentile, maybe print 75th percentile, which is NP dot percentile. Now you have to give marks, comma, which percentile you want, 75th, 25th, 50th, okay? 50th percentile is nothing but median, okay? So it will give me the 75th percentile. Okay. One NumPy concept that initially basically confuses beginners, but it is very important. It is access in Python. So let us understand it visually. See, there is a 2 by 3 array, which is 10, 20, 30, 40, 50, 60. Okay. When we use x is equal to 0, okay, it gives me, it will do the operation down the rows, effectively calculating column wise. Okay, if we are using x is equal to 1, it will be performing the operation across the columns, basically calculating row wise. Okay, so one simple way to remember is basically x is 0 collapses the rows and x is 1 collapses the columns. Okay, so if I have written ki from this array I need x is equal to say 0, so what will it give me? If x is equal to 0, it will give me everything down the columns. Okay, and if x is equal to 1, then it will give me everything down the rows. Okay, so let us try to do it in Google Colab. Let us print what my a is first. Let us see if I have anything in a. Okay, so we can directly print a dot, maybe the sum function along the axis equal to 0. Okay, now it has created the sum across the columns. Okay, so 3 plus 1 is 4, 4 plus 2 is 6. Okay, then maybe print a dot mean value along the axis equal to 1. So I want the mean along the axis equal to 1. Then it will give me the average value along the axis. I don't want the average value for the entire array. So it gave me 1.5 and 3.5. So 1 and 2 are mean at 1.5, 3 and 4 at 3.5. Okay. Next is basically we have to connect every dot we have learned so far. In real data science project, we rarely use NumPy functions in isolation, but we usually follow a workflow. Okay, so first we load or create our data, then we basically inspect what is the shape, what are the data types in it. We basically see if the data is all fine, or we provide filtering and masking to clean the data. If once I get the clean data, I transform it into the desired shape using reshaping and scaling, and finally do the exploratory data analysis to see if I want some statistics like mean, standard deviation, or something else. So this is where NumPy starts becoming more than just a Python library. It becomes basically a part of our data processing toolkit. Okay, let us try to do this entire thing. Okay, so how will you start? You will start with import NumPy as NP. We have already done that, and maybe we already have marks. Let us see, we have, yes, we have marks. Okay, then what we will be doing is we will be creating array. So we have already created something. We'll be seeing whether we can print, see what kind of shape it is having. So for that we can write marks dot shape, so that we can actually do something on it. Okay, so we have seen its shape. It is 6 elements. Okay, 6 by 1. Okay, and then we can maybe have average. Then we can also use filtering. Let us try filtering. So how many students are passed? Maybe the marks, where marks is say greater than equal to 50. Okay. So let us print this past. Okay. We can also do normalization and reshaping. Okay. So we have just used arrays, indexing, statistics, broadcasting style arithmetic, reshaping, and access in a one small workflow. Okay. Now this is for NumPy essentials. Let's quickly recap what we have learned. We started with NumPy arrays. We learned how to create NumPy arrays and then understand their dimensions and shape. Then we learned indexing and slicing. Then we done reshaping, vectorized operations, broadcasting. We also looked at Boolean indexing, iterators, generators, statistics, and concept of access. But NumPy is only the beginning, I'm telling you. We will learn about series, data frames, reading the CSV files, Excel files, selecting and filtering data, missing values, sorting, grouping, and much more. So if you're following the series, make sure you practice these NumPy examples before moving ahead. And remember, don't just watch the code. Open Google Colab, type it yourself, change the values, break the code, fix the errors, and experiment. That's where the real learning happens. Okay. I'll see you in the next tutorial. Thank you.